So for this one, the concentration of atmospheric carbon dioxide in parts after. So for this one, at first we're going to write it up algebraically by using the 2 points, the one at the very beginning at x equals 0 and 364, versus we're looking at the year 2200, which is going to be x equals 200, y equals 987. And those are the only 2 points that we're going to focus on right now to write our equation. Remember, c is our initial amount. When time t equals 0, our initial amount was 364, or mathematically, that's our y-intercept. So our next thing is to figure out what a is. So I'm going to go to the formula y equals, plug in my 364, a to the x, and then focus on my last coordinate that I'm using here, 200, 987. The 987 is the y value, or the output, and the input, or the x value, is 200. My goal now is to solve for a. So I need to get the a term by itself, and to do that I need to remove the 364. It's hooked by multiplication, so to undo multiplication, we divide. So divide both sides by 364. So I get a to the 200th power equals, and then take 987 divided by 364. I'm going to do that on my calculator here. So I got 987 divide 364. Right, and I get this big, huge, long decimal. Now I'm going to hold that decimal on my calculator, but I'm not going to write all the digits down here. I'm just going to write down a few, 2.7115, and then I'm just going to put some dots after that, indicating that it keeps on going forever. My a value, though, is raised to the 200th power. To get rid of a power, I take a root. So I'm going to go to the 200th root. So that's going to give me my a value. All right, so again, I'm going to use the calculator here. And on my calculator, I have to type in the root first, then go into the math function, or math editor there, and then go down to number 5. I've already typed in my x is 200, so I'm just going to push the number 5. Now that's not 200 times the root, it's the 200th root of, and then I want that whole thing. So rather than type it all in again, I'm going to do second, and then the negate key, because the second above that is, or the word above that is answer, and it's going to type that whole answer in under there for me, and then just hit enter. So my a value, rounded to 3 decimal places, is going to be 1.005. The number next to that is a 0, so we don't round up. It'll just be 1.005. Then I can go back to the function, and that kind of skipped around on me here. We're all having all kinds of technical difficulties. So then I'm going to plug back in f of x equals my c value, 364, and then it's times 1.005 to the x. So now they want me to use that equation from above to predict the concentration in 2025, rounded 2 decimal places. Remember though, I don't plug in 2025 for x. I know x is my years, but it's the years after 2000. So that would be 25 years after the year 2000 that I would be plugging in for x. So f of 25, that just means what's our function value in the year 2025 going to be. So I'm going to take my numbers here, 364 times 1.005 to the 25th power. And when I do that, you can type that out on your calculator and double check, it should come up to 2 decimal places, rounded, it'll be 412.34, and the unit label on that is parts per million, or I can just abbreviate ppm. Okay, that's what your Y value, remember, was representing parts per million of carbon dioxide. Okay. Let's put that in there. For part C, now you're going to use your calculator and the stat button and use exponential regression, EXPREG, to write the exponential function. So if I go in here to my calculator now, go into the stat menu, click on edit. Now I've already typed in my values. So at the year 2000, notice I didn't put in 2000, I used my number 0. 2050, I used 50. 2100, I only used 100. The 150, and then the 200. And then typed in the corresponding output or Y values. So to compute my exponential function now, I'm going to go back into stat, move over to calculate, and then I'm looking for EXPREG, exponential. So we need to scroll down. There it is, exponential regression. And press enter. And press enter again. See how it has my A, which is my initial amount, 364.044, a whole bunch of digits, and then my B value of 1.005000, a bunch of other numbers. So it's asking me to round all values to 3 decimal places. All right, so I'm going to round to 3, so that 4 is going to stay put, and this is going to be my function then. F of x equals 364.044 times 1.005 raised to the x. Okay. Let's scroll down a little further. For part D, they want me to use the function values f of x, or f of 0 equals 364. So that's the point when x is 0, y is 364. And f of 200 is 987. So that's just a fancy way of saying in the year 2000 it was 364 parts per million of carbon dioxide. In the year 2200 it was 987 parts per million of carbon dioxide. That's just another way of writing those 2 points. Write a linear function, which means this is what I'm looking for. F of x equals mx plus b. Right, so I need to find my slope. 987 minus 364. The change in y's over the change in x's. Compute the numerator, compute the denominator, and do my division. And when I do that, you should come up with 3.115. And since I'm writing a linear function, it's not necessary to put the unit label on here, but the unit label would be parts per million of concentration of carbon dioxide per year. But that's also my m value that I'm going to be plugging into the function here. The b value is your initial amount, which was 364. So your function looks like this. Okay. So again, the unit label on that average rate of change would have been parts per million of carbon dioxide per year. For our last question, which function, exponential or linear, best fits the data given, and explain why? Well, if you take a look at the difference in the years, all right, the difference in the values of the carbon dioxide in parts per million that you have here, and you start looking at what those numbers are. If I take, for example, the 467 minus 364, all right, I'm going to see a difference of, what, 103? And then if I take 600 minus the 467, I see a difference of 133. Not exactly the same number. But if I look at the ratios, in other words, if I take 364 divided by, I'm sorry, I want 467 divided by 364. That ratio comes up to be about 1.23. Right. And if I take 600 divided by 467, I get about the same ratio. So our ratios seem to be the same, whereas our difference isn't. So if our ratios are a better fit, then we're looking at an exponential function. Okay, and the reason why is all of our ratios seem to be about 1.23, and it's a constant, 1.23, versus the difference, which is not constant.